Hi, and welcome back to the second part of the tutorial on simple linear regression in R. As a reminder, simple linear regression involves predicting the values of one variable, the dependent variable, based on the values of another variable, the independent variable, using a linear equation. In this tutorial, we will continue using the marketing budget and actual sales dataset from Kaggle, and we will be exploring linear regression assumptions. Linear regression relies on several assumptions about the data and the model. These assumptions include linearity, independence of residuals, homoscedasticity, and normality of residuals. By checking these assumptions, we verify whether the data meets the conditions required for accurate regression analysis. If any assumptions are violated, it can lead to biased parameter estimates and incorrect inferences. To assess linearity, let's create a scatter plot of the dependent variable against the independent variable. Let's do it using ggplot2. We can plot the regression line using the geomsmooth function and passing the lm argument, which stands for linear model, to the method parameter. The relationship is linear as the data points roughly form a straight line pattern. Look for deviations from linearity, such as curves or clusters of points, which may indicate nonlinear relationships. Another way to check for linearity is to plot the residuals against the independent variable, or fitted values. Let's plot the residuals against the fitted values. In a linear relationship, the residuals should be randomly distributed around zero with no discernible pattern. Patterns in the residuals, such as a curve or funnel shape, suggest a violation of linearity. Independence of residuals can also be checked by inspecting the residuals plot. Ideally, the residuals should exhibit a random scatter around zero. If the residuals appear to be randomly scattered without any systematic trend or pattern, it suggests that the errors or residuals from the model are independent of each other. It's good practice to complement visual inspection with statistical tests, such as the Durbin-Watson test, to ensure the validity of the independence assumption. Running the test in R is pretty straightforward. First, you need to install and load the LM test library, and then run the test using the DW test function on the model that we created in the previous step. The Durbin-Watson test statistic ranges from 0 to 4. A value close to 2 indicates independence in the residuals. A value close to 0 suggests positive autocorrelation. A value close to 4 suggests negative autocorrelation. A small p-value suggests evidence against the null hypothesis of no autocorrelation, and a large p-value suggests no evidence against the null hypothesis, indicating that the residuals are independent. In our case, we have no evidence against the null hypothesis and can conclude that the residuals are independent. Homoscedasticity, also known as constant variance, is a key assumption in regression analysis. It refers to the condition where the variance of the residuals is constant across all levels of the independent variable. In simpler terms, it means that the spread of the residuals remains the same across the range of predictor values. To detect heteroscedasticity in the residuals of a regression model, we can run the Breusch-Pagan test. It assesses whether the variance of the residuals is dependent on the values of the independent variable. The p-value is less than the chosen significance level, commonly 0.05. You reject the null hypothesis of homoscedasticity in favor of the alternative hypothesis of heteroscedasticity. In our case, the p-value is less than 0.05, which indicates that there is evidence that the residuals exhibit heteroscedasticity. The assumption of constant variance is violated. We will discuss the remedy for this issue in the upcoming videos. The last assumption we will cover in this video is normality of residuals. There are several common methods for testing the normality of residuals. We will use the Shapiro-Wilk test, which is a statistical test used to formally test the null hypothesis that the residuals are normally distributed. The p-value associated with the test statistic is 0.1076, which suggests no evidence against the null hypothesis, indicating that the data may be normally distributed. Throughout this tutorial, we've explored the key assumptions of linear regression, including linearity, independence of residuals, homoscedasticity, and normality of residuals. Assessing and addressing these assumptions are crucial for obtaining accurate and meaningful results from linear regression analysis. If assumptions are not met, it may be necessary to take remedial actions, such as data transformations, utilizing robust regression methods, or adjusting model specifications. More on this next time.